Xianggu and I like Ansar.
All right, thank you, Marco. Good afternoon, everyone. My name is Xiang Yu from Arizona State University. I'm happy to be here to show you our work on CaVE. Is a constraint storage approach to handling integrity constraints. So I promise it's going to be simple and easy and quick. And hopefully by the end of the talk, you'll get some inspiration about using functional programming language scheme to implement some logic programming ideas. Okay, so the introduction here. The vision we have is like we try to compute the logic programs, in this case, in our case, definite program, normal program, and integrity constraints, just using resolution and unification. And also to retain their relational properties. We have a few steps taken so far. The first one is done by the mini-Cameron community, by Fritz Friedman and all, reviews the resolution and the unification, which can be easily extended and modified. Then we have the stable Camerons, extend the mini-Camerons with negation operators under the negation failure and the stable model semantics. Now this is our step right now. This is the CaVE. CaVE basically provides an integrity constraint support via external constraint stores. So main news we bring to the community. The first one is for the logic programming community. We added integrity constraints to a resolution-based system using constraint storage. To the functional programming community, we use macros and the continuations to build up constraints gradually. So some preliminary before jumping to the CaVE and its implementation is that, okay, the macro is the scheme macro. In this case, it supports the meta-programming things. We can construct and transform the programs. So one example we can use in logic programming is like the De Morgan transformation. So for example, you have any CNF or maybe DNF, you apply a negation to it, you want to change it to another form, it can be easily done by the macro and scheme, just one line macro. Okay. And the next one is a continuation. So continuation is just a special term for a partial function that waits for some values. So for example, in logic programming, it's a substitution set between each code functions. So during the proving process, we try to prove a sub-code to be true. So you are waiting the substitution to be updated by the previous proving process, right? And once you prove it, you're passing down this substitution set, like updated substitution set, to the next code functions. So continuation here is basically just connecting all these like small pieces together. So using these two ideas, mini-Cameron basically uses a macro to transform the goal function by attaching this like implicit substitution set into it. So all the goal function can be connected. This is how all the resolution process is getting started. Okay. Then stable Cameron based on this one, they extend the mini-Cameron to handle negation in normal programs. And once we handle the normal programs, this is the operators that provided in mini-Cameron. Rafi already introduced this something, the equal signs for unification, Fresh to introduce the temporal logic variables, and the count D to represent the disjunction. Like for one goal to be true, you may have multiple ways to prove it. We use count D to represent it. Then for the conjunction, basically you naturally we move it from one goal, moving to the next goal. So in stable Cameron, we provide models for negation under the NAF and the SMS, and we have to define the goal functions. Okay. Now here's the connection between the logic programming, the FLoC syntax, to the stable Cameron syntax. On the left-hand side, we have the FLoC style LSS programming code saying, okay, if Alice can go somewhere, if not Bob is not going. So written down in the stable Cameron format, it's like define, oh, Alice is not a vowel. It's a slightly extended, but this is the whole program. It's basically making a choice like, okay, we can only choose one Alice or Bob to go to numbers, but they cannot go in at the same time. Okay. Now we know in this kind of normal programs and with the integrity constraint, we will be able to generating and eliminating combinations. So this is the idea by Lin and Zhao proposed back to 2004 to say, okay, if there's a loop involved the even number of negations in it, it will be able to generate the combinations. And the odd negations of the loops of the negations will be eliminated. So Here are some examples on the propositional cases. So basically change the address above into the peak and not peak. In this case, it's free. So we can have binary choices, like for example, it's going to be peak, it's not peak, it's free. We can also have the combination of the choices. So we extend the propositional logic to regular logic variables. So in this case, the variables has no domains. But we need to provide the domains to it, which can be done by through a set of facts. So for example, in this case, we can say X is a set of numbers ranging from 1 to 3. Okay. Now, as we already be able to generate our combinations, now we want to use the integrity constraint to eliminate them. So integrity constraint basically just control the outcome of the goal in an odd loop form. So we can do one thing that, okay, we don't want to pick anything. So if the pick is true, the integrity constraint say, okay, this cannot be true. It means like we cannot pick anything. It must be free in this case to compute the models. Okay? So this is the one way to write down the integrity constraint. There's another way, because in top-down solving or in the stable cavern settings, we need a goal function, which is, in this case, is headless, is unable to create a goal function. So we need to transform it to the equivalent form. It's like, okay, so it's fail, and take, and not fail. This is the odd loops over there. So the equivalent way, but it will be able to allow us to write the kind of the head functions in the top-down solvings. But unfortunately, even if we can write down this function, using the resolution, we're still unable to prune out the unwanted models. We'll tell you why. There's some problem in the resolution. So even though, like, okay, for example, I extended it into the two-dimensional way. Previously, we only have pick one variables, but we can right now have pick two, and we connect them together. Basically, this is kind of Queen's problem. We're saying, okay, these two cannot be picking on the same row. Okay, this integrity constraint enforce that. If you try to use the resolution to solve it, the resolution will be unable to handle it. The main reason is the resolution's minimum model trait will ensure that it binds the minimum number of variables to approve the minimum number of the subgoals to be true. So this is all the minimum model semantics behind the resolution. Okay, we try to use them as minimum as efforts to satisfy the rules. So, but in this case, in the previous, like the normal program cause cases, resolution works because it attempts to prove each subgoal, and the process will continue after proving the subgoal until all the subgoals are proved, right? But in the integrity constraint, it's contrast cases. If some subgoals, for example, if all the subgoals in the integrity constraint have been proven to be true, the resolution process should be terminated. So this behavior is different than the original resolution behavior. So we either change the semantics of the resolution, or we treat the integrity constraint as kind of some exception to the original resolution. So just like in your programming language, you write in Python, you have a regular routine. In our case, it's a resolution, and we have the exception routine. In our case, it's the integrity constraint. And it turns out, in functional programming, they don't have exceptions, but we can use continuation to simulate exceptions. So this is how all ideas connect together. So mainly because the resolution in this case, it will still tend to leave the variables in the predicate integrity constraint unbound to satisfy it. So for example, these rules, if the resolution tries to do nothing, this constraint will not be violated, and resolution will be happy. So okay, we continue moving on. But in fact, we want to check this constraint is there any violation or not. So this is there are two approaches to try to handle it. So already, like one thing is like we can do the grounding, like linear way, or the translating is a SAS and SCAP ways to do it. So back here, for the grounding cases, still using this numbers, there's three numbers. Okay, so it's 3 by 3, you produce 9 symbols. We will have a peak 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, all the way to peak 6, 3. Okay? And in this case, the grounded integrity constraint will have like this 18 rules in total. And for the SAS, we use the translate integrity constraint by using the false, just create a dummy head and still try to use the resolution to solve it. As we mentioned before, resolution cannot handle these cases. That's why, like here, you need to introduce the CaVE. So the CaVE basically rewrite the integrity constraint into two parts. One part is the emitters, and the other part is the verifiers. So for an emitter is the head of the normal program class that emits values. So it should be the truth value and the symbols. So in our case, it's like, for example, the peak, free, and numbers. All these three can be used as emitters. Okay. Then for the emitters, we can further categorize into two parts. One is the constant emitters, which means it only emits values. So this case means, like, for example, if I have a 3, 2, 1. So this case, the 2, 1, there's no free variables in there. It's already constant. So 3, 2, 1, in our CaVE representation, you only emit truth value. So as soon as we prove the 3, 2, 1 to be true, okay, you emit the truth values. And another case is like we have variable emitters, so we can emit the truth value as well as the symbols to the unique variables. So for example, the peak xy. So in this case, it can emit truth values as soon as the xy unifies with some values. It can be 1, 2, 1, 2, 3, or anything. So as long as the peak xy unifies the xy with some values, it emits truth values and the corresponding symbols. Okay? Now, we have introduced the emitters. Now we have the verifiers. So in this case, verifiers becoming very simple. It's just a Boolean expressions that will receive the values from the emitters. Okay. So in our case, so for example, the later part x equals y u, the y equals equal to v, the v is forming the verifiers. We concatenate them together, forming the constraint handlers. So once we have the constraint handlers, when the emitters emit values, so for example, when it's peak 1, 1, peak 1, 2, then the constraint handler will get its values, then we can evaluate this like pending result. Okay, so same thing, just the different values examples, but I'll skip that. And to implement these ideas, it actually turns out to be simple and easy if we use the continuations we introduced before. So here is the new syntax we introduced to the stable Cameron. This constraint blue part is the emitters, origin part is the verifiers. So basically the verifiers right now is the continuation. We don't have the value for xu and the yv provides to it. So it's just like waiting for some values. So one way to do that, like we can manually wrap it through some of the lambdas. So for example, like a lambda like this, we'll say, okay, lambda x and y, we're passing the xy with the value 1 and 3, and we're passing a value u and v with 2 and 4. So once we have complete values to this continuation, this whole expression can be evaluated and produce the true or false outcome. Okay, now we just need to plug these things, mechanism, into the program to let the solver handle it automatically. So to do that, like without human involvement, this is I'm writing the code. And back to the macro application, macro will allow the program to handle this meta program, modify or update this continuation. So here we have a new macro to wrap this anomalous lambdas. This is what the macro looks like. We have the expression, we have parameters and values. We just wrap them together. So with that, we can use let the machine or the solvers to do the things. So instead of manually writing down the lambda, we're just calling this macros 2 times. We're producing the same updated lambda functions. So once the constraint handler receives the values, it can be still the same. Okay. Now we have this internal representation. We'll break down to the 2 lists. One list is the list of the emitters. It will emit the truth values and the symbols. The other part is the constraint handlers. So first, if we emit peak 1, 1, now the emitter list will getting shorter. Then we have 1 there now. And the CC is the constraint constructor we just created. We can call CCXY is 1, 1, updating the constraint handler. And eventually, when it's becoming an empty list, we get a result. Okay, that's another cases to do the running times. All right, some conclusion, the contribution. Basically here we just introduce a new approach to handle integrity constraint, treat them as the exception to the resolution process, and create an external constraint storage. In our case, it's basically just a continuation. And we use a lot of like macros in the continuation to do our implementations. Like previously, in Cameron, we use macros to connecting the functions. And right now, we can use it to creating and updating the constraint handlers. And previously, continuation only used to connecting the internal flow function representation. But here we also use it to store the constraint and populating the constraint handlers. So some future work is like you can add some soft constraints, because right now it's just hard constraints. We can have like delay evaluation. We can add optimizing heuristic search to it, because right now all the algorithms are like bottom up. We can come up with a new way to do it top down using the macro or the configuration here, which will be much better. And then we can add a CLP into it. Like here, like the delay CaVE. I think previous talks just talk about how can we have this delay constraint to support in the CLP. We can add it into it. We can use ECAVE. And we can use right now. We can use iterative constraints with definite programs without the indications of math and SMS. Only classical indications in the verifiers. Okay, thanks for your time. Happy to be here.
Questions? Yes, please.
Your systems is implemented in functional language or
My
is it
system.
language that you are using to implement the listener?
What system do you use to implement for language?
The language that you are using to make the implementation.
Implementation is Steam. Is the R6 Steam. It's a functional programming.
Functional language.
Yeah.
And how do you compute the stable models when you have even loops?
Yeah, we have even loop, so we can create a co-inductive tabling to remember the calls and to count how many indications involved.
And generate a list of answers, or
This
how do you make the non-deterministic answers?
non-deterministic answers. Basically, this search is guaranteed by the mini camera already. The search is complete search, so you can try all the different combinations.
Okay.
Yes.
Thank you.
Other questions? If not,